Hi y'all, welcome back to the second installment of this video series here. We're going to talk about some sampling methods, particularly random sampling, and talk about different types of studies like experiments and properties of those. So let's jump into sampling. Next, we're going to kind of switch gears to talk a little bit more about sampling, and in particular, we've kind of talked about a little bit why we sample, but we're going to also look at some sampling techniques that are used in the field. Well, we've already mentioned that it is often impossible to collect information from an entire population, but we want to get info from a population. So we sample, and hopefully that sample is representative of its population. The way that we ensure that that is met over time is through a process of sampling at random. That is the process used to select the individuals from the population in a non-biased fashion. The main idea there is that every member or every individual has an equal chance of being selected. Okay. Let's talk about some of those methods. The main method, the primary method, is called simple random sampling. And this is sort of the technical definition, and we're going to break it down, where it says a simple random sample of size n, so n is representing a number, selected from the population is one in which all possible subsets of the population of that size n have an equal chance of being chosen. Let's break that down. Suppose you have this limited population, pretty easy, A, B, C, D, just 4 letters. And let's suppose we want to select a sample of size 2. Well, we need to list all samples of size 2 to demonstrate simple random sampling. There's kind of some rules here. You cannot have a sample, for instance, AA. That doesn't work. Furthermore, AB, BA is just a rearrangement of the same thing. So here, these are all unique combinations of samples of size 2 from A, B, C, D. Now notice, count them up. There's 6 of them. So what we've done here is we have listed all possible subsets of size 2 from this population. And since there's 6 of them, if each of those has a 1 in 6 chance of being selected, that means the sampling method is a simple random sampling method. So this is called simple random sampling. It's kind of the go-to and easiest random sampling method. And basically, this is kind of the technical definition as mentioned, but basically it boils down to, hey, everyone's got the same chance of being chosen. So that's the go-to method. Let's look at a few other methods. The other methods that we're going to touch on are stratified, systematic, and cluster random sampling. These are just a few sampling methods that we will discuss briefly. Sometimes disciplines have their own sampling protocols that are specific to their field of study, but these can be applied in all sorts of disciplines. All right, let's go. Let's look at stratified sampling first. A stratified sample is first you divide up the population into non-overlapping groups, or strata, or subpopulations. Now, non-overlapping, so an individual cannot exist in 2 groups at once. Okay, so once you've grouped up the population, then you take a simple random sample from each of those groups. So in this figure here, this population has been divided into 4 groups, and a little bit was simple random sampled from each group. Then all these individuals compose your sample. What's beneficial about this method is that it guarantees that each group is represented in your sample. A caveat about stratified sampling is that the individuals in each of these groups usually have to have some sort of similarity amongst them. And so in this little picture, you see the top rectangle has stars, the second rectangle has squares, and then triangles, circles. So there's some sort of way that this group is similar to each other, and some way that this group is similar to each other. Let's look at an example. Okay, a political survey. If the respondents needed to reflect the diversity of a population, the researcher would specifically seek to include participants across all races and religions that are existing in the population, and that would be in proportion to the total. So a stratified sample from a population that accomplished that would probably be a more representative sample than that of just regular simple random sampling. So here the groups would be different races or religions or even genders, and the sample is composed of a simple random sample from each of those groups. So it sounds a little complex, but I think this little image is very useful. Okay, let's look at another one. Systematic sampling. This is when every nth individual is chosen from the population. So the way this usually looks is like every 6th person is chosen, or every 18th house is selected. Now it doesn't sound super random, but where the random component is inserted is where the starting point is. So you start at your selection process at a random location, and then you make your selection at regular intervals after that. So every 6th dog or whatever you are sampling. This is also a pretty easy sampling method, as you can imagine. Quick example. Suppose you want to sample 8 houses from a neighborhood of 160 houses. Well, you would choose every 20th house after a random starting point. You probably wouldn't want to start with your house or your best friend's house. You want to, because you might be inserting bias into that. But you'd want to select a random house to begin with, and then choose at regular intervals, i.e. every 20th house. Okay, let's look at the next sampling method, cluster sampling. So this starts out similar to stratified sampling at first, in that we divide the population into subgroups or clusters. So in this diagram here, we've got the population divided up into, it looks like 5 groups. Now this time, what is going to happen is a simple random sample of the groups is chosen. In this little diagram, it appears that this group was chosen, and everyone in that group comes into the sample. And this group was also randomly chosen, and everyone in that group goes into the sample. So we collect a simple random sample of the groups and then select all the individuals in those chosen groups. Here's an example. Suppose we divide the students in our class into clusters, such as the freshmen are a cluster, the sophomores are a cluster, juniors, seniors, and grad students, etc. Then we say we're going to perhaps randomly select 2 clusters. I'm just pulling out the number 2 from nowhere. So all members in those 2 clusters would form the random sample. So it would potentially be a group of all sophomores and all graduate students, or the sample would be composed of all juniors and all seniors. So it grabs up the entire group. Okay, those are our new sampling methods there, and let's look at an example outside of the definitions of those sampling methods and see if we can identify which sampling method is used. Okay, a high school principal polls 50 freshmen, 50 sophomore, 50 juniors, and 50 seniors regarding policy changes for after-school activities. Okay, so here's our list of methods we've discussed: simple, cluster, stratified, or systematic. Well, it might be nice to see which methods can we eliminate. It doesn't seem like every 10th student was chosen because we weren't told any of that info. So I don't think it's systematic. And furthermore, it seems like every group, every grade was selected from. Ooh, so it seems like they were grouped. Okay, so that's going to narrow it down to either cluster or stratified, because those are the 2 methods that have groupings. Now, a little bit of each group is composing the sample. So that's going to narrow it down to stratified. Sweet. Okay, let's look at one more method, but this is not a random sampling method. This is a convenience sample. A convenience sample is one in which the sample is obtained easily and not based on any random procedure. Some examples of this are where volunteers are utilized for the study, or the individuals are self-selected in some way. Because the sample is not based on randomness, these types of samples are generally not considered to be representative of the population. And when that occurs, that means that there is some bias in the sampling method. So I call that a 4-lettered word, the B word, bias. And we're going to talk a little bit about bias and sampling error now. The concept of sampling error is always present due to the process of sampling, right? A sample is collected, hopefully through random sampling, but to learn about the population. But a sample will never exactly resemble that population. So there will always be differences between the sample and the population. In general, the larger the sample, the smaller this difference will be between the sample and the population, thereby decreasing the sampling error. So sampling error is always going to be present and to be expected. We say that the sample, if it is randomly selected, then these differences are due to random chance. So we sometimes call this random chance error. It's to be expected. However, if the sample is not random, then those differences, that error, could be due to some other factors such as bias, which is a tendency for some values or individuals to be selected at a higher chance than others. And if there is bias in the selection process of sampling from a population, then any inferences or conclusions made from that could be incorrect or inconsistent with the population. Let's look at some examples in which sampling error would be exasperated. So my question to you is, are the following brief scenarios going to result in a representative sample? 800 volunteers are recruited from local nightclubs to evaluate a new treatment for social anxiety. All right, that's all we're given. So I want you to think about, okay, local nightclubs is where the sample is coming from. And furthermore, they're volunteers. But the study is going to evaluate the effectiveness of a treatment for social anxiety. So here I would say no. This sample is, well, composed of volunteers and is sampling from individuals who attend nightclubs. So that's probably not going to be the population who consumes social anxiety medication. Presumably, I could be incorrect there. But I would say no on this scenario. Let's look at another one. To investigate factors affecting first-year success of students in the CSU system, that's you, researchers selected a simple random sample at the end of the school year from the population of all students who had just completed their first year at a CSU campus. Okay, we're going to dissect this a little bit and look at a contrasting scenario. So they want to see what affects the first year success students. All right, they got a simple random sample. That sounds good. And this is from a population of students who just completed their first year. Okay, so let's contrast that with this next scenario, which looks very similar but it's slightly different. We're going to investigate the factors affecting first year success. This is the same from the population of students who had started that year at a CSU campus. So the difference between these two scenarios is that this top scenario is from the population of students who completed the first year. And this one is from the population of all students who had started that year at a CSU. So one of these is going to result in a more representative sample than the other. Can you think about which one of these scenarios is going to result in a sample that may not include the desired population? Let's consider who starts the year and who completes the year. If you're only selecting from the individuals who completed their first year, then you are going to be excluding a group of individuals, potentially the group of individuals who dropped out, transferred out, or could not complete their first year for a number of reasons. So this top scenario here will not result in a representative sample of students to investigate first year success, because this second scenario will include those individuals who potentially did not finish their first year. And that is particularly relevant for the study question of factors affecting first-year success. Let's look at another one. A researcher wants to select a sample of households in Arcata for a study of energy usage. She lists every house in Arcata by street address, then randomly selects 50 houses from this list. All right, well, let's see. This researcher, she wants to get a sample of houses across Arcata. It doesn't seem that she's going to neglect any household or dwelling by listing all the addresses and randomly selecting from that list. So this one seems pretty good. Thumbs up. One more. To determine the average cost of a 2-day stay in a hospital in Massachusetts. Typo. The researchers survey 4 hospitals in Boston using simple random sampling. Okay. The researchers here want to discuss the cost associated with hospital stays in Massachusetts. However, their sample is only including hospitals in Boston. So they're not going to include hospital stays outside of that major city. So I would say this sample would not represent hospital stays throughout Massachusetts, but only in Boston. So no on this one. Let's briefly discuss random sampling in the context of inferential statistics. We mentioned a goal in sampling is to have a sample represent its population, so that any trends that were observed in the sample can be extrapolated to its population. Now, observing any trends in the sample are of value in and of itself. We called those descriptive statistics, but we also, if possible, would like to draw conclusions beyond the sample to its population, and the only way that that can be accomplished is through random sampling, because it is that randomization that allows us to ensure that the population is represented in the sample. So it is also important to define your study population very specifically. You usually want to include some sort of sense of time and space into your study design. Some of the examples given in the previous slide would not meet these minimum requirements. If we backtrack for a second, these are all very, very brief descriptions just to kind of get the point across, but each of these lacks a temporal specification, such as what year did this occur and where. The very last one we have Massachusetts and Arcata and the one before it, but like this first one, it only says local nightclubs. So where is that applying to? So it's important to have time and space explicitly mentioned in your study, so if there are any inferences that can be made, that we know to exactly which populations they can be made to. Okay, I think that's a good segue to our next topic, which is about variability or variation. And variation is an idea that is also present in any data set. For example, height of students at HSU. Height would be the variable, and everyone's height is different. They vary, right? And so one of our tasks is to describe the trend of height with that variability ever present. So variability is present within samples, but it is also present across different samples. For instance, suppose Anna and Jose both collect a simple random sample of 50 heights of HSU students. Then, both Anna and Jose calculate the average height. Will these two sample statistics be the same? Well, no, right? Anna and Jose are going to be collecting samples that are most likely very different, and the sample statistics from them, the average height, are also going to differ. Now, the purpose of collecting the sample is to learn about the population. Would either of their sample statistics be incorrect? No, they were both legitimately sampled and calculated, but this demonstrates how there would be variability across different samples even though they were collected from the same population. That's part of that sampling error. What if they collected samples of size 100 instead of 50? Well, they would be collecting more information about the population. So we would expect that the sample statistics would probably be closer to each other, both Anna and Jose's. And we would also expect that those sample statistics would better approximate the population parameters. So variability, a concept that we are going to discuss over and over again throughout our course. Let's look at another sampling example. And we're going to talk about marbles in a cup. Classic example. So suppose you got 10 marbles, 3 red, 7 black, and you're going to select one at random. Pretty fun stuff. What is the chance of selecting a red marble? Well, there's 3 reds out of 10. So 3 out of 10, 0.3, 30%. Those are all the same value. What would be the chance of selecting a black marble? Well, 7 out of 10, 70%, 0.7. Sweet. Let's suppose that you selected a red marble. You're a lucky person. Now, keep that marble out of the cup. Throw it out the window. Now, what would be the chance of getting a red marble from that cup? Well, there used to be 10 marbles total, but you just threw a marble out. So now there's only 9. And how many of them would be red? Well, you threw a red marble out, so now there's only 2 red marbles out of the 9. What about black? Still, there's 9 total, but there should still be 7 black marbles. What I've just demonstrated is the idea of sampling without replacement. Once an individual is selected, it's removed from the population and cannot be chosen again. So that's kind of classic. You don't usually select, say, the same person twice, because that individual does not exist twice in the population. So that's the classic sampling protocol. But of course, there is a name if that is not used, sampling with replacement. So that's not typically performed. And that's when, if you took that red marble and you put it back in the cup, that's not typically used, but we've got a name for that. Moving right along, let's talk about different types of studies, such as experiments and observational studies, and some of the elements within them. We've discussed types of variables already, such as quantitative and qualitative or categorical, but we're also going to talk about how variables occur in the context of studies. a variable can wear a couple hats at a time. So a variable can be quantitative, continuous, but also be explanatory. A variable can also be categorical and also be a response variable. So what do I mean by explanatory and response? I kind of think about this as like the x and the y variable, x, y, where an explanatory variable is like the independent variable or the input, and the response is like the output or the dependent variable that may be influenced by the explanatory variable. Here's a brief example. Does vitamin E prevent optic nerve damage? With this little bit of info that we have here, can we identify what the explanatory and response variables would be? Well, what is of primary interest here? Is it the vitamin E or is it the optic nerve damage? Based on this very little info, I think the optic nerve damage is of primary interest, and it could be influenced by vitamin E. So vitamin E is the explanatory, and optic nerve damage is the response. Now that we have discussed variables and the way that they occur in the context of a study, let's now talk about those studies. For instance, the classic experiment. An experiment is a study where there's some control being exhibited because the researchers are manipulating explanatory variable or variables or imposing particular conditions on the study subjects. So this is the classic lab environment, but it does not have to occur in a lab. But if you think of a lab, you know things are very controlled and accounted for. Experiments. We'll look at an example shortly. Let's contrast that with an observational study in which the researcher is still collecting data and information from subjects, but not by manipulation of any variables, but only as a passive observer. And so there is not any control in an observational study. And we're going to discuss how in an experiment, if it's performed correctly, a cause and effect relation can potentially be discovered because of that control that was exhibited. But that cause and effect cannot be discovered in an observational study for a slew of reasons that we will discuss right now. Observational studies, because information is collected as the world is turning and not because of any control, sometimes they're considered less powerful because of confounding or lurking variables that can occur. And confounding or lurking variables, they have different names, are variables that are not considered in the study but may affect the response variable of interest in the study. A confounding variable then may impact the response variable of interest in such a way that you cannot distinguish its impact from the explanatory variable of interest in the study. Let's look at an example. You want to investigate the effectiveness of vitamin E in preventing optical disease. Cool, we've thought about this already. So you recruit a group of subjects and ask them if they regularly take vitamin E. You notice that the subjects who take vitamin E exhibit better optical health on average than those who do not. Okay. Does this prove that vitamin E is effective in disease prevention? Not necessarily, because this is not an experiment. This was an observational study where a bunch of subjects were just asked, hey, do you take vitamin E? And then they possibly did an eye exam. So there are a lot of differences between the two groups that were compared outside of just vitamin E. People who take vitamin E may also take other steps to improve their health: exercise, diet, other supplements, etc. And any one of those factors could influence their optical health. So all these other things here, diet, other supplements, those are confounding variables that are present such that it's difficult to discern the effect of vitamin E on optical health. Typically, observational studies have a lot of lurking or confounding variables because the environment is not manipulated or controlled, thereby making it difficult to discern if is it truly vitamin E that is causing improved optical health. It's hard to distinguish that since there's so many differences between these two groups of individuals who take the supplement and those who do not. So a cause and effect relationship is not possible in observational studies. That doesn't make observational studies bad. Sometimes that's all you can do in a particular research question. But let's contrast with experimental studies. In an experiment, it is possible to utilize a randomized design in which each subject or unit is randomly assigned to a treatment. There are subjects. They could be people, they could be plants or dogs, and they are exposed to different treatments. Maybe one group of subjects will take the red pill and another group of subjects will take the blue pill. This allocation of subjects to these different treatments, i.e. the red pill or the blue pill, that is the control that researchers are imposing. And ideally, that these individuals are randomly distributed to these two groups, red pill or blue pill. We'll talk about that in the future. But in general, an experiment is when subjects are manipulated in the sense that they are placed in certain groups in order to experience different treatments. This random allocation of the individuals to the groups allows the researcher to assume that the only difference between the groups is the one that is imposed, i.e. the treatment in group 1, the red pill, and the treatment in group 2, the blue pill, so that the individuals in each group exhibit features that are present in both groups and intermixed. For instance, you would not want the red pill group to only be males and the blue pill group to only be females. If that was the case, now gender is a confounding variable, because the differences between red pill, blue pill might not be because of the pill, but it could be due to the gender. You would probably also want a mixture of ages or other background information, again, so that way the groups are pretty similar and the primary difference between them is the treatment that was imposed upon them. that is the backbone to a randomized design in an experiment that allows for a cause and effect relationship to be discovered between explanatory and response variables. The groups are pretty similar. The main difference between them was the treatment that was imposed. Let's talk about some of the terminology that I've thrown around, but I have not yet formally defined. We've mentioned the word treatment. Those are the different values of the explanatory variable. So that could be red pill or blue pill. That could be a high dose or a low dose of some chemical, or even a control group, where this is some group that serves as a baseline, so that way other groups can be compared to the control group. For instance, maybe you've got a group that is going to be exposed to a large dose of insulin, and that's their treatment. You've got another treatment group that's experiencing a low dose, and then you'd probably have a control group that is exposed to none of the treatment, so that way the other treatments can be compared to. I've thrown around the words subject and experimental unit. Those are the individuals, the people, or the objects that are participating in the study. Another fun concept here you may have heard of is the idea of a placebo, where a placebo, it looks like the real thing, tastes like the real thing, but it's not the real thing. Sometimes people call this the sugar pill, although I doubt sugar is actually used because that can have a chemical response. It's usually some sort of inert substance, maybe even a saline injection. And you've probably heard of the placebo effect, which have been shown to have a lot of surprisingly effective results. These are just some numbers I've seen in some studies. Placebos have been effective in helping with wound pain or seasickness or headaches. It's pretty interesting. There's even something called a nocebo effect, nocebo, where individuals who are given a placebo even experience side effects associated with the real drug. Some individuals have even demonstrated objectively observable side effects such as hives or itchiness. It's pretty interesting stuff. Let's talk about another property present in experiments, that of blinding. You may have heard of blinding before. There are generally two types. We have single blind, where the study participant is unaware of the treatment that they are receiving. And then there's double blind, where the individual, again, is unaware of the treatment that they're receiving, but also the individual who is providing the treatment administrator, does not know what they are administering either. Why would this procedure be implemented in an experiment? Well, the power of suggestion can be quite strong, where we want to minimize the chance that an individual perhaps behaves differently if they know what treatment they're receiving. So we want to minimize that, which is why the participant would be kept in the dark about what they're receiving. But all right, well, why would we want the administrator of the treatment to also be blind to what they are administering? That is so that the administrator also does not treat the participant any differently based on what type of treatment they are providing. I would imagine that any legitimate researcher would not treat individuals differently depending on if they were given a placebo or the actual treatment, but inadvertent cues can be delivered, such as through body language or vocal intonation. And even if those types of cues were not delivered on purpose, a participant in the study might detect those, and that could sort of throw things off. And so doing a double-blind procedure will help minimize those effects. Let's look at a little example that outlines briefly the details of an experiment in which volunteers were randomly assigned to a treatment group or a control group that took a vaccine or a placebo for the common cold. And these were self-reported and compared to the number of colds they had in the current year compared to a previous year. The group that was exposed to the vaccine had a 70% reduction on average. And that seems pretty convincing until you look at the placebo group, and they had a 69% reduction in the number of colds. Without this placebo group or control group, you wouldn't have any sort of comparison between how effective this vaccine supposedly was. So often the placebo or the control group can serve as a baseline for the active ingredient group, i.e. the vaccine here. Now there could be difficulties in this study, such as these are self-reported. If people knew they were in the placebo group or the vaccine group, they might behave a little differently in their behaviors. So there's a lot of things to consider in the design of a study, but a placebo group can be used as a baseline to compare the other treatment groups to. That's going to conclude this second video. I'll remind you that the corresponding PowerPoint is on my Open Math. And so what should you work on next? Well, this should be our first week of class, and so I would like you to explore our course page on my Open Math and see all the tools that are available to you, and just get accustomed to the organization of where things are and what to click. The first homework assignment, I'm calling it Homework 0 because it is based on the syllabus and not based on stats, really. That is due the first Friday of the semester, and if you could start the homework for Experience 1, that is due the following Monday. And this homework assignment is going to be based off of this PowerPoint and the previous PowerPoint, so the past two videos. So hopefully you are well prepared for that. And thanks for watching. I'll talk to you soon.